Hello and welcome to Empowered Learning. This series of videos will be about rational functions and how to graph rational functions without a calculator. As you see, we have several different objectives that we need to learn for this. And so we're going to break up this entire lesson into probably 3 or 4 sessions. So the very first one, we will talk about recognizing a rational function when we see one, as well as figuring out what the domain of a rational function is. The next series will be about all the various properties that we look at when we see a rational function, and figure out how that rational function needs to look to be able to see those properties. And then, of course, the last lesson or lessons will be examples of how to put all of this information together to be able to come up with a graph of a rational function. So let's go ahead and get started. So simply put, here, when we go and talk about rational functions are just polynomial fractions. Simply put, that's really what they are. They're just polynomial fractions. In order to recognize what a polynomial fraction is, we first have to recognize what a polynomial is. And so if you don't really know what a polynomial is or don't know how to recognize one, please check out my videos on the properties of polynomials so that you can learn that and thus understand what I'm talking about here. If you're already familiar with polynomials, then you have a good idea of what I'm talking about. In short, we just want to make sure that for our rational functions, a numerator is a polynomial and our denominator is a polynomial, but we do not want our denominator to equal 0, okay? Because we know that whenever we have that type situation that we have something that's undefined. So to get some practice on this, we're going to look at these particular functions and determine which one of these are rational functions and which ones are not. So if we look here in the beginning for part A, we see that this function, we have a polynomial on top and a polynomial on bottom. And so the reason that we know we have a polynomial in the numerator and the denominator is because all of our exponents are whole numbers. All of our coefficients are real numbers, and that's both for the numerator and the denominator here. And our denominator does not equal to 0. So this is a rational function. Part B, that function is also a rational function as well. We see that for part B's function, we just have our polynomials in the numerator and denominator factored out. And this is actually the preferred way that we want to look at our rational functions whenever we're trying to sketch a graph of them, because they allow us to be able to see everything that we need to. So this is a rational function as well. For part C, this looks like a normal polynomial. But if you notice here, if I was to take this and divide it by 1, then technically that would be a polynomial as well. And reason being is because in my denominator here, I could rewrite 1 as just 1 times x raised to the 0, which is technically a polynomial. And so from this, what we realize is that every polynomial is also a rational function, but not every rational function, like this example and this example, is necessarily a polynomial, okay? So for here, this is a rational function, okay? For D, we see that we have a fraction, sorry, not a fractional exponent, but a negative exponent in our polynomial that we're looking at in the numerator. So because we have this negative exponent here, we would want this to be a polynomial, but it is not, okay? So I should have said just expression in the numerator. So our numerator here is not a polynomial because of that negative exponent there. So of course, that makes this not a rational function. Here we have square root of x. And of course, that would make the expression 2 times square root of x not a polynomial. And thus, our function f of x here is not a rational function. For f of x is equal to 1 over x, this is a well-known function known as the reciprocal function. And this is the quintessential rational function. Okay? And again, 1 could be considered a polynomial, and x is also a polynomial. It is just a polynomial of degree 1. Okay? So here, f is indeed a rational function. So now that we sort of have an idea of what a rational function is and what it isn't, the next thing that we're going to do is move on to what the domain of a rational function is. Okay? And so, domain of a rational function, we basically just look at the denominator. And so whatever values of x make the denominator 0 is what we want to exclude out of the domain. It'll be everything else included. So for example, for the function for part A, we know that x minus 5 is not allowed to equal to be 0. So if we add 5 to both sides here, we see that x is not allowed to equal 5. And of course that's true because if we plug in 5 right there, that makes our denominator 0. And of course we can't have that because that means that the function is undefined at that particular x value. So because of that, we know that our domain is going to be all real numbers except for 5. And so we could express that this way in set notation, or we could do it this way in interval notation. And let's clean up that last thing there. That didn't come out too well. Okay. All right. So for the next one here, we want to factor this out. And if we factor it out, x squared minus 16 is just x plus 4 times x minus 4. And so here we see that if we plug in a 4 for this x, that the denominator will go to 0. And negative 4 here, it will go to 0. So we know that we are not allowed to have values of negative 4 or 4. So in that case, we know that our domain is going to be all the x values that are not equal to negative 4 or 4. And so we'll write this way. Hopefully I'll be able to fit it all on here. Okay. For our next example, C, if you notice here, we still look at the denominator here, and we know that we cannot plug in a negative 5 here because, of course, that's what makes the denominator 0. And so the domain for this would be all real numbers except for negative 5. Okay. And of course, for this last one here, we know that if we plug in 0 right here, that wouldn't work. And of course, if we took 2x plus 5 and said it can't equal 0, then of course, if we subtract 5 from both sides and then divide by 2, we see that x is not allowed to be negative 5 halves, or negative 2.5. So for this very last one here, we see that the domain is going to be all x values except for -5/2 and 0. Okay? So we'll start off with -5/2. Go to 0, and then from 0 to infinity. So that's what our domain would be. So now I want to call your attention to the graphs of 1 over x, which is called the reciprocal function, and 1 over x squared, which is called the square reciprocal function. I know I've renamed these the wax on, wax off function and the band conductor function because of how they look. But mainly speaking here, we want to recall these type of functions because they play a huge role in being able to have us be able to graph rational functions that are a little bit more complex later on, especially when we start to talk about the behavior around a vertical asymptote. And we'll learn what a vertical and horizontal asymptote is here in just a second. So in general, our functions, the way that 1 over x squared and 1 over x looks, the reason why they look the way that they do, and I'm going to erase all this stuff here so that we can see it more clear. So if you notice here down at the bottom, I have x is equal to 0. That is a imaginary vertical line that the function 1 over x and 1 over x squared has that sort of acts like a wall. And so it's saying that, hey, as our function gets closer and closer to that value of x equals 0, the function either has to go down to negative infinity or positive infinity. So it has to try to, in a sense, go under the wall or go over the wall, but it cannot go through the wall. Okay. Similarly, we see that we also have another asymptote called a horizontal asymptote. And for both of these, they also share one of y equals 0 as well. And that's better known as the x-axis. And so what the horizontal asymptote does, it says for very large values of positive or negative x, the function that we have tends to act more and more like that function. In this case, y equals 0 for very large values of positive x and or very small values of negative x. So on the next page here, we'll get a better idea of what that actually looks like. Okay. So in general, an asymptote occurs when for some value x approaches positive infinity, x approaches negative infinity, or x approaches some specific value. A function f of x approaches a fixed horizontal or vertical line. Okay. And so I have a list here of what these things look like. And what I'm going to do is go down to the actual graphs themselves and talk about that. So in figure A right here, this is an example of what we call a horizontal asymptote. And it's a one-sided horizontal asymptote, meaning that as x gets infinitely large, the y values for this function tend to get closer and closer to y equals 2. Okay. So for part B, this is what's called a horizontal asymptote as x approaches negative infinity. And so you see for this one that as x tends to get more and more negative, the y values start to get closer and closer to 5. Hence why the horizontal asymptote is called y equals 5. If you notice for A and B, that in these cases, the function is not crossing the horizontal asymptote. However, if you look at figure F, Figure F is another example of a horizontal asymptote. And you can see this one is synonymous to what we call in engineering the drum whack function or the sync function. And so here you see how the horizontal asymptote is the x-axis, but you see how this graph continues to oscillate but gets smaller and smaller as it as x gets infinitely positive and as x gets infinitely negative. And so the point of this is that there is a myth that horizontal asymptotes cannot be crossed, and that is not always true. It really does depend upon the function itself. For A and B, those are examples where we have a function where the horizontal asymptote cannot be crossed. For F, however, we know that the function can be crossed there. Okay. So moving on to vertical asymptotes, we see that example C and example D give us good examples of a vertical asymptote. And so actually this is incorrect here, so I need to correct this. This should say F and that should say C, like that. And this should be E right here. So C and D are actually examples of vertical asymptotes, okay? And so you can look at this and basically you see that as x approaches 6 from the left side and from the right side, this asymptote is the type to where the function on both sides goes up to positive infinity. Here, for D, this is the type where both sides of the function, as x approaches -2 from both the left and the right, goes down to negative infinity. Okay? We do have other types where, let's say on the left side, and I'll just go ahead and draw a quick one. Let's say on the left side it goes up to positive infinity, but on the right side it goes down to negative infinity, and vice versa. Okay? So the idea here is just to give you an example of what these things actually look like. Okay? The last one is an example of what we call an oblique asymptote. Okay? And an oblique asymptote is an asymptote that either looks like a line or some other function that we know. And the way that we know that we have an oblique asymptote is that the degree of the polynomial in the numerator is larger than the degree of the polynomial in the denominator. And so we will get further into that in some of the other videos. But this, I just wanted you to know how it looked. Okay. All right. So we are going to cut off this video here, and we will start the second video on some of the properties, and we'll start off by locating poles.